Hey everybody, welcome back to Applied Econometrics. This week we're going to talk about Chapter 11, Regression with Binary Dependent Variables. All right, so in prior chapters, what we did is we introduced binary regressor variables in multiple regression models to allow for a richer set of controls. Right, so including things like degree status, gender, class size thresholds we talked about, and other dummy variables. Right, this helped us explore interesting ideas and new control variables on the right-hand side of our regression equation. Now, up until now, we've had continuous dependent variables, or that left-hand side variable, in our regression models. But in this chapter, we're going to allow our dependent variable to be binary. Right, so this allows us to ask other interesting questions that we so far have not been able to inquire about, such as what are the factors that impact whether someone gets a loan? Right, it's kind of like a yes, I get a loan, or I don't. What is the impacts, the things that impact whether or not a student is admitted to a graduate program, or is someone a smoker? Right? Each of these dependent variables are kind of like a yes, no, or a 0, 1 variable, and we're trying to find the independent variables that are impacting the likelihood or the probability of success. All right, so specifically, in each of these questions, the dependent variable, or that left-hand side variable of interest, is a binary variable that takes one of two values. Either it's a 0 or a 1, or alternatively, you can think of it as a no or a yes. So we're going to explore a handful of these types of models that allow us to investigate these types of regressions, including linear probability models, probit models, and logit models. Now, in looking at this binary dependent variable, we're also going to explore a new empirical example in this chapter, one that's going to look at the factors that impact if someone gets a loan for a mortgage for a home, and whether or not there's systemic racial bias in mortgage lending. Now, in this example, the dependent variable as to whether or not you get a loan is yes, you get a loan, 1, or no, you don't, 0. And we're going to try to identify what are the factors that impact the likelihood of you getting that loan. Sometimes they are continuous variables, like your financials or your credit score. Sometimes they are binary variables. Are you married? Yes or no. Are you of a certain race? And we can kind of code for that. Right, so incorporating both binary variables on the right-hand side as far as regressors, we've done that many times, but now we're kind of switching gears ever so slightly and making our dependent variable one that's binary in nature. So we can ask these yes and no questions, what impacts the likelihood or the probability of something being true? All right, so the outline for this lecture is to first talk about the linear probability model. Think throughout the lecture in the book, you'll see L, PM. And this will be an easy but kind of naive approach at taking an estimating procedure when the dependent variable is binary. Again, yes, no. Then we'll talk about a more refined approach using probit and logit regression. We'll discuss estimation, whether or not it's going to utilize OLS or not. And then we will talk about the application to racial discrimination in mortgage lending. Now, up until now, we've looked at our dependent variables as being continuous in nature, right? We said, what are the factors that impact the district-wide average test scores? That can vary between 0 and, let's say, 900, right? It's a continuous measure of aptitude. Or what are the factors that are going to impact the traffic fatality rate? And the traffic fatality rate is, again, a continuous measure of the danger on the road and how it's going to translate into fatalities. Now, these are continuous variables because they can take a spectrum of values. Now, that's all well and good, right? A lot of interesting questions have continuous dependent variables, but some interesting questions have dependent variables that are actually binary in nature, right? So they don't take many values. They take actually two values, 0, 1, yes or no. All right, so we have 3 different examples right here. Circle them in blue. All right, number 1, do I get into college or not? Right, what are the factors that impact the likelihood that I get into college? Well, getting into college is a yes or a no. Did it or did it not actually happen? Okay, so we can code that as 0, 1. And we know there are a host of independent variables that impact the likelihood of you going to college or getting into a particular school. It can be high school grades, SAT scores, demographic variables. And what's interesting here is with high school grades, and SAT scores, so GPA and SAT, these are continuous independent variables. Whereas demographic variables, might be binary in nature, right? Or they might fall into certain categories for dummy variables. So we've looked at both continuous and binary variables in the right-hand side of our regression equations. We've done that. Okay, we're comfortable with that by now. What's slightly different here is now our dependent variable takes on one of two values. And we can also look whether or not someone smokes or not. During an undergraduate faculty student research project I had a few years ago, I had a student who had been a smoker, and he was curious about the undergraduate characteristics that lead to whether or not someone smokes or not. Looking at financial history, looking at grades, looking at psychological measures, looking at ethnicity and things like that. And we know this dependent variable, though, is do you smoke or don't you? This is a 0, 1, a yes or a no variable. Now, this might depend on cigarette taxes. This might depend on income. This might depend, again, on binary demographic variables. So again, our right-hand side variables are both binary and continuous, but now our dependent variable, now whether or not you smoke, is now binary. Now, we can use the same right-hand side variables, the independent variables, to answer a related question. How does these independent variables, how do they impact the amount that we smoke, where our dependent variable would then be continuous in nature? Or we can slightly modify the question and just say not how many packs a day do you smoke or how many cigarettes do you smoke, which is continuous, but instead, do you smoke or not? So we can use the same exact rich data that we've collected to answer very related but different dependent variable type questions. Now, lastly, we have below whether or not your mortgage application to get a loan for your home is accepted or not. And this again is something yes happening or no happening, a 0 or 1 coded variable. Now, it might depend on your race. It's probably going to depend on your income. It's going to depend on a lot of things. This is the empirical example that we're going to tackle a little bit later in this chapter. Now, looking ahead, the empirical example that we'll use looks at the factors that are going to impact whether or not your mortgage application was denied. All right, so our dependent variable is equal to deny, and that'll be coded as equal to 1 if yes, we were denied, or equal to 0 if no, we were not denied. Actually, our application was accepted. And we're going to look at the degree to which income factors and race may play a part in deciding this dependent variable. Now, the book makes use of some really interesting data that was collected by the Home Mortgage Disclosure Act, HMDA. And what it did is it looked at almost or a little over 2,000 individuals, and it characterized their likelihood of actually being accepted or denied a mortgage application based off of their financial indicators and their demographic indicators. Now, for context, what's really important to acknowledge is these applications were not collected from nationwide surveys. Instead, they were collected from single-family mortgages made in 1990 in the greater Boston area. All right, so we'll come back to this point later, but we have to think about when we are deciding whether or not there is an income effect on whether or not you are approved or denied a mortgage loan, and whether or not there are racial impacts as well. This particular data set will speak true statistically to this particular area in the country and in this particular year, and we have to question whether or not that's truly externally valid across different cities, different states, and different time periods. Right, but we'll consider that a little bit later. Now, for reference, our dependent variable, again, is the mortgage denied or accepted. So our dummy variable will be deny. And we'll try to control for as many variables on the right-hand side, things that we can observe and quantitatively measure that were collected in the survey. Things like income, overall wealth, your employment status, and other types of characteristics regarding the loan and the home as well. And then also of particular interest, at least with this question, is race important for predicting the likelihood of being denied a mortgage loan or of being accepted? All right, so let's go ahead and start off with the most simple case. Let's look at linear regression model with a single regressor. All right, so we're going to deal with one independent variable, for right now, xi. Now the question is, how do we interpret this coefficient? In traditional linear models that we looked at, let's say in chapters 4, 5, 6, and 7, we said that the coefficient represented the incremental change in our dependent variable when you change our independent variable by, let's say, 1 unit. Right? So if I increase x by 1, then I can anticipate a beta 1 change in my dependent variable. Right, but that was the case when our dependent variable, our y, was continuous, right? Because we could see this increasing by a point here, 3 points there, 2/10 there, because this variable is a spectrum of potential values. But what does then our beta 1 coefficient actually mean when y instead is binary, right? It's a yes or a no. It's a 0 or a 1, right? If beta 1 is equal to 0.3 and I increase x by 1, does that mean it's going to increase my probability by 0.3 of getting the loan? Does it decrease the probability? What is the exact relationship here? Now, after we actually estimate our coefficients, what we like to do then with these empirical results is we like to say for certain values of our regressors, of our independent variables x, we like to say what is the predicted value of our dependent variable? Well, here's the thing. Our dependent variable is either 0 or 1. For every single person, did you or did you not, let's say, get the loan? Did you or did you not get into the school of your choice? It's a yes or a no, a 0 or a 1. So what then does it mean if we estimate a regression equation? We put in our estimated coefficients, we put in some values of our regressors for x's, and then let's say our predicted value is, let's say, 0.26. What exactly does that mean? I thought it's a 0 or a 1. How can I not get the loan 0, get the loan 1, or 0.6? Is that something in the middle? What does that exactly mean interpretation-wise? So these are questions we need to acknowledge and we need to kind of discuss before we actually start tackling this type of model. Now let's go ahead and give some thought to how exactly do we interpret coefficients in a model where our dependent variable happens to be binary. Now, I think what's helpful here is to reflect on from the traditional simple linear regression or multiple linear regression, right? What exactly are we trying to estimate? Right? What do our models, what do they yield? Well, we're always trying to estimate the value of our dependent variable given our actual independent variables. So what is the expected value then, traditionally, of y given x? And we traditionally see that as, let's say, beta naught plus beta 1 x1, where beta 1 can be seen as the impact of x1 on modifying the predicted value of our dependent variable, y. Now, that's the case when our dependent variable happens to be continuous. What happens then when our dependent variable happens to be binary? Again, 0 or 1. So we're going to now introduce this idea of what's called a linear probability model. Right, so the general idea here is the predicted value of y, sometimes written as y hat, is going to be interpreted as the predicted probability that y is equal to 1. And beta 1 is the change in that predicted probability for a unit change in x. So we're still playing this game. If x changes by 1 unit, ... how does our y variable change? Okay. Whereas before we used to say, well, if beta 1 is equal to 0.2, that's going to increase our dependent variable by 0.2. All right. But that's when we have a continuous dependent variable. Here, we're now interpreting that beta 1 as the increased probability of our dependent variable being equal to 1. Okay, so to what degree our independent variable x is going to either increase or decrease the likelihood of success or a 1 coding for our dependent variable. So a simple example here might be if x happens to be income and beta 1 is, let's say, equal to, let's say, 0.5, and let's say income is measured in thousands of dollars. Let's say if income then increases by $1,000 and our beta 1, at least in this situation, is 0.5, then we have that an increase in our income of $1,000 is going to increase the probability of our dependent variable being equal to 1 by, let's say, 50%. So if our independent variable happens to be income, and let's say again our dependent variable happens to be the likelihood of getting a loan, let's say in this situation, then increasing income by $1,000 will increase the probability of getting a loan by 50%. Now going back to the math, let's say we have a regression That's given by beta naught plus beta 1 xi plus ui for the error term. When y happens to be binary, right, if we're still trying to figure out what is the expected value of y given x, well, y takes on two values. Sometimes it's 0, sometimes it's 1. All right, so to find the expected value, or think about this from your probability and stats classes, the expected value happens to be the value that that variable can take times the probability that x is equal to that value. Here we're going to do the same exact thing. The expected value of y, given x happens to be, well, sometimes y happens to be a 1, and we're going to multiply by the probability that y is equal to 1, given our independent variables. And then sometimes our dependent variable happens to be 0. We're going to multiply that by the probability that y is equal to 0, given our independent variables. Right, so we have then that this part right here will just go away since it's multiplied by 0. So we can say that the expected value of y given x happens to be the probability that y is equal to 1. So translating that down here, when we're looking at our beta 1 coefficient, we're seeing the degree to which this independent variable is going to increase the likelihood that our dependent variable actually is 1. Right, so we talked about the mortgage example. Let's say we're talking about, getting into the school of your choice. We can have our independent variable, let's say one of them being whether or not you volunteered. That could be a binary independent variable. And the beta 1 coefficient on whether or not you volunteered, let's say is 0.3. This suggests then that volunteering will increase the likelihood of you being accepted to college, so y is equal to 1 by 30%. This gives us an idea as to the impact of our independent variable on our binary dependent variable. Right, so what we're doing now is we're thinking about this beta 1 increasing or decreasing the probability of something happening or not happening, depending on how it's coded. So what we're doing is we're calling this the linear probability model, at least in this example. Since on the right-hand side, we have a linear representation of our coefficients and of our independent variables, right? Beta naught plus beta 1 times x. And on the left-hand side, we have the expected value of y interpreted in this case as the probability of y being equal to 1. What's the probability of success of being a smoker, of getting a loan, of getting into college? We now have a linear probability model. Now specifically, in mathematical terms then, we can think about beta 1 as having a marginal effect on the probability of our dependent variable being equal to 1. All right, so we can say for a certain level of x, let's say x is equal to little x, what is the probability that our dependent variable is equal to 1? All right, but what if we change our independent variable by, this is that right-hand side variable, what if we change it by some delta x? Right, we change it by 0.1, we change it by 0.3, we change it by 1. Okay, we're changing the level of our independent variable, and I want to know how is that going to change the likelihood of our dependent variable, the binary one, being equal to 1. So beta 1 then is the change in the probability, the marginal probability, comparing the new probability, subtracting the old probability, and dividing by that change in x. Usually the change in x, we like to say, is usually 1 unit, just to keep things simple. All right, so everything in this bottom equation is actually very familiar to you, but we've been thinking about things as x changing and that changing my dependent variable that happens to be continuous. Now, because our dependent variable is binary, and it's a yes or a no, a 0 or a 1, we're thinking about it in terms of the likelihood or the probability of success when y is equal to 1. All right, so when I change x by a marginal amount, let's say delta x or 1, how does that change the probability of me getting that loan or me going to college or me being a smoker? Right? How does it change the probability of y being equal to 1? Now, while the original data that we're going to look at a little bit later had over 2,000 observations, let's just kind of reflect on what the linear probability model looks like when we're looking at a subset, let's say 127 data points. And this is a simple characterization of it because we are only actually incorporating one right-hand side variable, right? Only one independent variable here. And that's going to be the PI ratio. where that's going to represent the ratio of debt payments, monthly debt payments to income. Right? When you are buying a house, someone who's trying to generate your loan thinks about what is your monthly income and how does your monthly responsibilities towards your mortgage compare to your monthly income. Right? If your income is, let's say, $5,000 and your monthly payment for your home mortgage is $4,000, that's 80% of your income. Can you really survive on that for the duration of the loan? Probably not. They typically try to target a PI ratio of about 0.3 to 0.5 as being something standard, something safe, where the bank believes that you have the capacity of spending 30 to 35% of your monthly income on mortgage, and you have 60 to 70% left on intangibles, everything else. But that seems like something that people can sustainably pay over the duration of their loan. Now that's our independent variable on the right-hand side, down here. And our dependent variable is, again, binary in nature, whether or not you are denied or not denied for your loan. Now, again, think about this. PI, when this is a low value, versus PI, when it's a high value. So low value, we have a small percentage of monthly income going to, let's go income. This goes to your mortgage payments. Whereas if you have a high value, then a significant percentage, a large percentage of, let's say, income goes to payments. Again, thinking about this from the bank's perspective, if your PI ratio is relatively low, you have a lot of money left over to pay for everything else that's important in your life. You are someone who's seen as a stable investment. When you compare that to someone who has a high PI ratio, a significant portion of their monthly income is going to their mortgage payments. So we think about this in terms of stability. If someone has a crazy month where they have higher than expected costs in a host of different areas, can they still make their mortgage payments? Well, it's going to be really hard when your mortgage payment is 80% of your monthly income. Okay, so you are seen as a high-risk individual with a high PI ratio compared to anyone with a low PI ratio. So let's see whether or not this idea kind of translates into the likelihood of you getting a loan or being denied. So we see down here, for relatively low values of the PI ratio, right, again, individuals that don't have to pay a significant fraction of their income to their mortgage, we see that they're kind of bundled down here, where the probability of being denied is actually relatively close to zero, or exactly equal to zero in this case. Now, we can compare that with higher values of the PI ratio, where you're paying between 35 and, let's say, almost 70% of your monthly income just to your mortgage. Those individuals are quite frequently denied their mortgage loan. Now, overall, since we have this linear equation right here, this linear regression line, estimated regression line, we see that there is a positive relationship then between higher PI ratios and an increased probability of being denied a mortgage loan. Right? So that makes sense intuitively. If you are seen as somebody who has to pay a significant portion of their income to your mortgage, you are seen as someone kind of unstable and at high risk. I'm probably not going to, as the mortgage lender, give you a loan, because I'm kind of scared about the potential for you to default on the loan. As opposed to the comparison, people with low PI ratios have a much greater likelihood of avoiding being denied, or similarly, being accepted for their mortgage loan. Let's go ahead and look at a particular example here. Let's say when the PI ratio happens to be 0.3. All right, so again, this is the world where you're paying 30% of your monthly income, potentially to the repayment of your monthly loan. All right, so at 0.3, we go up to the estimated regression line. And this says, well, something kind of weird, right? We're not being denied entirely, right? Our dependent variable is not 1, and we're not being Instead, what we can do is we can interpret the 0.3 for the PI ratio, hitting our estimated regression line at 0.2 as being the probability that deny is going to be equal to 1. So here, if your PI ratio happens to be 0.3, then the probability that deny is equal to 1 is going to be about 20%. So that's relatively low. As opposed to, let's say, if we are at a PI ratio of, let's say, 0.5, let's say this hits around right here, let's say 0.7, why not? This suggests that if your PI ratio happens to be equal to 0.5, then the probability of you being denied a loan happens to be about 50%, or excuse me, about 70%, right here. All right, so we're not going to say this is going to happen with 100% certainty. Again, this is a dependent variable that is binary in nature. Again, 0 or 1. We're going to interpret the slope of the line, or these estimated points right here, as being the likelihood or the probability of our dependent variable being equal to 1. So we again see for relatively high values of the PI ratio, it's going to be more and more likely that the loan will be denied. Now, instead of just looking at that subset of the data sample, now let's instead look at the full data set. And again, we're trying to estimate the relationship between, let's say, the PI ratio and its impact on the likelihood of being denied a loan, where again, our dependent variable is binary in nature. So let's say we estimated this regression, and we have that the coefficient on the PI ratio is 0.604. We have our constant intercept being negative 0.08. And we can ask ourselves, what is the predicted value for a PI ratio equal to 0.3? What's the likelihood of me being denied a loan based off of this estimated regression? All right, so I'm going to plug in the 0.3 equal to the PI ratio. So we have negative 0.08 plus 0.604 times 0.3, and that gives me 0.101. Now, what this says to me is if your PI ratio happens to be 0.3, then this means you have a 10.1% chance of your application being denied. So you can multiply this by 100% to convert that decimal to a percentage. We have 10.1 percentage points. So again, let me restate that. If your PI ratio happens to be 0.3, there is a 10.1% chance of your application being denied. Now we're focusing on your application being denied because our dummy variable is coded as a 1 if you're denied and a 0 if you're not denied. So this is always going to be the probability of y being equal to 1. And here y happens to be denied for your application. Now, in addition to using this estimated regression to calculate predicted values, we also want to clarify whether or not this particular independent variable happens to be significant. So even though we have a binary variable as far as our left-hand side dependent variable, the reality is that we're going to interpret t-stats and p-values in a very similar fashion to what we've seen in every single prior chapter. So here I'm looking at the coefficient, estimated coefficient, and the standard error. And we're going to find that the t-stat is just north of 6 right here, which suggests that our PI ratio happens to be significant at the 1% level. All right, so we have PI being significant at the 1% level. I think the t-stat is something, well, it's greater than 6, so that is relatively high. Now, because it's a significant variable, this suggests then that individuals that have a higher PI ratio, this is going to significantly increase, since this is a positive sign, or at least it should be, this is going to significantly increase the likelihood of being denied that mortgage loan. Now, in addition to calculating predicted values of our dependent variable, we can also say, well, how does our dependent variable change when our independent variable change? So here, what happens to our likelihood or probability of being denied if our PI ratio goes from, let's say, 0.3 to 0.4? And again, from the perspective of the mortgage lender, you are now becoming a higher risk of default if a greater percentage of your monthly income is now going to your mortgage payments. Okay, so if you're becoming more of a risk, then the likelihood of you being denied a mortgage loan is probably going to increase. At least qualitatively, that's what we assume to be true. Let's quantify that now with our estimated regression equation. So cleaning this up here so we can see it. All right, so I'm going to plug in a 0.4. Actually, it should be right here. This is a typo. So we want to estimate what's the probability of being denied when our P-I ratio is not 0.3 but 0.4. Whoops. Okay, so we're going to plug that in. This is going to change right here, and we're going to get 0.162. So in this world, if your PI ratio happens to be 0.4, then the likelihood of you being denied alone is just north of 16%. All right, so thinking about this in totality, the effect on the probability of being denied alone when you increase the PI ratio by, let's say, 0.3 to 0.4 is going to increase the probability of being denied by 0.061. So what is that? We have probability of deny when x is equal to 0.4 minus probability of deny when x is equal to 0.3 is equal to 0.162 minus 0.101, and that's going to be roughly equivalent to 0.061. Now we could have also calculated that effect. So calculating this effect right here, saying, well, if I'm going to prospectively change my PI ratio by 0.1, then the effect on our likelihood of being denied, so that probability is equal to 0.1. Since we're going from, what are we doing? We're going from, where is it? 0.3 to 0.4. So this is plus 0.1. So we're going to do 0.1 times the coefficient. The coefficient happens to be 0.604. 0.604. And this is going to be roughly equal to 0.06. So again, what this says right here is if I decide to change my PI ratio by, let's say, 0.1, it's going to increase the likelihood of being denied by 0.06 or by 6 percentage points. So it's increasing the likelihood of being denied by that quantitative amount. Now, in the prior slide, we looked at the impact of a financial indicator on the likelihood of being denied. Let's extend this question and also look at the degree to which other demographic variables might influence the likelihood of not getting a loan. So here we're going to look at whether or not there is racial bias. All right, so we are going to characterize each of our individual applicants here, at least in this example, as being black or not. So we have black being equal to 1 if they are, 0 otherwise. So we have these two categories in this simplistic example, and we're going to update our estimated regression equation. Now, one thing we'll say is we still have a positively significant PI ratio. This is still going to be north of 6 for the t-stat. So PI ratio is still going to be significant, let's say at the 1% level. But looking at this new dummy variable, we're going to have 0.177 divided by 0.025. And that's going to be something north of about 7. So we have black also, so this dummy variable, this also being significant, let's say at the 1% level. And it happens to be, let's undo that, it happens to be a positive coefficient. So this suggests by itself that individuals that are black, individual applicants, they have a higher likelihood of being denied. Upwards of 17.7 percentage points more of being denied relative to their counterparts of those that are coded as not black for this example. Now let's look at how this translates into the actual predicted probability of being denied. So again, let's go back to a world where we're looking at strictly 0.3 being the PI ratio. And I want to see how having a black applicant versus a non-black applicant is going to change the likelihood or the probability here of being denied a loan. So what are we going to do? We're going to plug in the 0.3 for the PI ratio, and we're going to plug in a 1 for this dummy variable, since this applicant is indeed black. And we're going to see that their estimated probability of being denied, based off of two things, their PI ratio and being black, is 25, well, north of 25%. Right? So right there, that doesn't tell us a lot, but we want to compare that to what is the estimated probability of being denied if you are not black. Right? So we're going to have the same exact financial indicator of 0.3 for the PI ratio, but now we're going to code black as 0 for this, let's say this white applicant. And we're going to see that the probability of being denied is, well, now 0.077, or just shy of 8% likely that you're going to be denied. So looking at just this number right here doesn't tell us a lot, but we have to compare that to its baseline comparison. So looking at black versus non-black, holding every other independent variable constant. So when you subtract the 0.254 minus the 0.077, we're going to get that the difference happens to be, well, shouldn't be surprising. It's going to be the coefficient on black, or 17.7 percentage points. Now, I don't know about you, but that so far is a convincing story that there actually might indeed be some racial bias when we're deciding whether or not someone is going to be approved or denied a loan. Because if we hold every single other indicator here, just the PI ratio constant across individuals, and the one thing that we modify happens to be the racial status of this individual, this suggests that individuals that are black are almost 18% more likely to be denied a loan. That is significantly higher. All right, but one thing we should consider is the reality that in this simplistic model, there's only two independent variables that actually impact the likelihood of being denied. Here, one financial indicator of the PI ratio, and then two, whether or not you're black. That's probably missing a lot of the important variables that are going to impact the likelihood of being denied or not. So there's plenty of room for omitted variable bias. We're going to explore that in the coming slides. Now, the linear probability model is the most simple and straightforward application of a model that's trying to understand and to estimate a model with a dependent variable that is binary in nature. Right? And what we saw right now is that the linear probability model has the probability as a function, as a linear function. This is important, as a linear function of x's. Right? So again, it was the probability where y is equal to 1 given x. That was simply equal to beta naught plus beta 1 x1. You'll say, that doesn't look like anything different than what I've seen before. And I'll say, I totally agree with you. This is all linear in the coefficients and linear in the x's. Right? This is not squared. X is not transformed to be, let's say, the natural log. So it's linear in the independent variables, and it's linear in the coefficients as well. And there's nothing interesting going on. This is very similar to, let's say, chapter 7 with multiple regression. Now, the advantage of this model is that it's going to be very simple to estimate and to interpret, especially the coefficients. We've done this many times over in pretty much every chapter up until now. And the inference or the statistical significance of these individual coefficients is going to play out just like we've seen before as well, assuming that we actually have heteroscedastic robust standard errors, right? So comma robust in all of our regressions. Now, the problem is that this linear probability model, because it has a constant slope right here, let's say beta 1, that by definition is going to assume that the change in predicted probability for a given change in x is the same for all x's. Right? So let's think about this. So this is going to be nonsensical. Think about somebody who has, let's say, a 0.1 PI ratio. So they pay only 10% of their income to their mortgage. And when they go from, let's say, 0.1 to 0.2, that is going to increase their likelihood of being denied, but not by much, you'd figure, because it's still only 20% of their income. Now, the linear probability model says that that change in income will change the likelihood of denial of the application the same exact amount as if someone went from, let's say, 0.7 to 0.8. Another example can be, let's say the industry standard for a safe mortgage loan, let's say, is a PI ratio of 0.3, and a dangerous loan is, let's say, anything greater than 0.3. So going from 0.3 to 0.4 might significantly increase your likelihood of denial by a large amount, since you go from essentially being someone safe to being kind of dangerous as far as the loan goes. Comparing that sizable increase in magnitude of being denied compared to, let's say, if you were, again, 0.7, 0.8, going to 0.9. Right? If you're already at 0.7 PI ratio, the likelihood of you being denied is significantly high. Are you going to be really any more likely to be denied if you go to 0.9? No, because you're pretty much being denied 100% of the time. The linear probability model says that this change from 0.3 to 0.4 in your increase in likelihood of being denied is going to be the same exact change as going from, let's say, 0.7 to 0.8 or 0.8 to 0.9. when you and I know that's most likely not true. Also, another big problem about the linear probability model is sometimes it predicts probabilities that are actually less than 0 or greater than 1. All right, so I brought this over from the prior slide. And we see, at least according to this estimated line right here, this blue one, we see that when the PI ratio, let's say, is 0.5, or going to be 0.15, then the estimated likelihood of being denied is actually something less than 0. So if you have a significantly low PI ratio, the likelihood of you being denied alone is going to be effectively 0. But this says it's not 0, it's actually less than 0. How can that be? And I'll say to you, and we should agree, that's not possible. So the linear probability model does something very funky with extreme values of our independent variable on the left and also on the right-hand side as well. This says that if the PI ratio happens to be, let's say, something north of 0.6, let's say it's at 0.7, this says the probability of you being denied is actually greater than 100%. It's something like almost 100 and almost 120%. That can't be. All right, so the linear probability model is very simple and natural to use as an extension of our multiple regression analysis, but it has some funky qualities that we don't love, in it being a constant slope, which is problematic, in the change in the probabilities, and also predicting some probabilities that are both negative and also greater than 1. That's going to be an issue. Now, what's nice about this is, as simple as this is, we do have some very approachable solutions to deal with these nonlinearities. And we're going to see that in both probit and logit regression. All right, so turning our attention then to improved models, again, probit and logit regression, recall the main problem with linear probability models, this is the LPM, is that these models identify the probability as being linear in x. So as x goes from 0.3 to 0.4, it's going to have the same impact as going from, let's say, 0.4 to 0.5 or 0.7 to 0.8. This can't be true, right? Instead, what we want is we want the probability to actually be increasing in x, and we want the probabilities to be strictly contained between 0 and 1. Right? It can be 0, it can be 1, it just can't go lower than 0, and it definitely should not go greater than 1. So what we want is a slightly improved model that's going to satisfy both of these conditions. And here we're going to see it's going to look something like an S-curve. So visually, the probit and the logit model actually look very similar, and we'll talk about why the two actually exist a little bit later. But effectively what we have is the same exact independent variable on the bottom axis, the PI ratio, and we have the same dependent variable, deny. But if we fit a probit model, well, what we see is that the slope is not constant. Okay, that's good. We see that the probability of being deny is increasing in x. So for very low values of x, right, having a PI ratio between, let's say, 0.2 and a little bit north of 0.3, your likelihood of being denied is relatively low. But as you go from, let's say, 0.3 to 0.4, from here to, let's say, here, your likelihood of being denied is actually going to go up very quickly or in a nonlinear fashion. And then as we go between 0.5 and 0.6, well, if you're already paying 50% of your monthly income to your mortgage, the likelihood of you being approved for a loan is already relatively low. Here, the likelihood of being denied is it's actually north of 80%. And you going from 0.5 to 0.6, well, you're already being pretty much denied at 0.5. You're almost definitely going to be denied at 0.6, but it's not going to change drastically. So we're not going to see a large difference here. Right? But overall, what we do have now is a nonlinear impact of increasing our horizontal variable x and its impact on the probability of our dependent variable happening, here deny. Right? So that's good. So we have nonlinear changes, and we have that our probabilities are contained between 0 and 1. So even when the PI ratio is something like between 0.1 and 0.2, we still have this not dipping below 0. Right? Just because you have a PI ratio that's relatively low, let's say at 10% of your income, doesn't mean your likelihood of being denied should be negative like we saw in the linear probability model. That was a big problem. Right? What's a negative probability even really mean? As opposed to when you have significantly high PI ratios, so let's say something north of 6, we should have that the likelihood and the probability of you being denied is not greater than 1 or greater than 100%. It should be effectively equal to 1. And what we see is that this is going to taper off at 1 right here. So we then have for all x, our probabilities make intuitive sense. It can't go below 0 and it cannot go above 1. Right, so these are the two necessary conditions that we had problematic with the linear probability model. As awesome as it was, we had some intuitive issues with that particular approach. And what happens here is that with the probit and the logit regression, that fits kind of like an S-shaped curve right here, we can now fix those those issues. All right, so let's remember where we were. So the linear probability model estimates the probability that y is equal to 1 given x being equal to a linear combination of beta naught plus beta 1 x1. Right, so this is linear in both the coefficients and the independent variables, betas and the x's. Now what the probit model does a little bit differently is it models this probability, so it's still the probability since our dependent variable again is 0 or 1. It's modeling this probability using now the cumulative standard normal distribution. Right, so phi z evaluated at z is equal to beta naught plus beta 1 x. Right, so this looks familiar as it does up here. But what we're going to do is we're going to evaluate this with the CDF of the standard normal distribution. So highlighting what we have now, the probit regression model then is still the probability that our dependent variable is equal to 1 given our independent variables. But now it's a nonlinear function of beta naught plus beta 1x evaluated according to the cumulative standard normal distribution. And we're going to see a handful of examples coming up shortly. All right, so we're going to call this little portion that's in here beta naught plus beta 1x. We're going to call that our z value or our z index, just depending on the textbook, of our probit model. So let's say right now, for the sake of an example, we have that beta naught is equal to -2. We have beta 1 is equal to 3, and our decided level of our independent variable happens to be 0.4. So if we're thinking about the example we've been kind of running through, we can say this is a model that's trying to understand the likelihood of being denied a loan. Let's say if your PI ratio happens to be 0.4. Okay, so what we're going to do is we're going to first evaluate what our z value is. Right, so we're going to plug that in to beta naught plus beta 1x. We're going to plug in the values that we have right here. And then we're going to evaluate that z value according to the cumulative normal standard distribution. Right, so we have -2 plus 3 times 0.4. That's going to be -0.8. And we're going to evaluate it according to the cumulative normal standard distribution. All right, so let's go ahead to, I think it's table 1 of the appendix, which will give us an idea of the area underneath this standard normal distribution. That's going to be to the left of -0.8. Right, so again, this is appendix table 1. Welcome. You find that in the back of your textbook. And again, this is for the cumulative standard normal distribution, whereby we're assuming that the mean is 0 and the standard deviation is 1. Again, we're going to evaluate this problem right here at -0.8. All right, so we have -0.8 right here. And then there's nothing beyond the 8, so we're just going to have 0.2119. So what that says to me right now is, according to our example, if we have the coefficient estimates for beta naught and beta 1, and we decide we're looking at the likelihood of denial if our PI ratio happens to be 0.4, we said, well, if that's the case, then our z is equal to -0.8. And according to the cumulative standard normal distribution, we have the probability of being to the left of that being 0.2119. Or this says when PI ratio is 0.4, this says the likelihood or the probability of being denied a loan happens to be 21, or let's say 2%. So this is the probability here. Probability of denial. Now, again, the main benefits of this particular approach is it satisfies those two necessary issues that were problematic with the linear probability model. Again, that model assumed a constant rate of change between x and our probability of denial, or our dependent variable. That's problematic. And it also generated negative probabilities and probabilities that were greater than 1. So this S-shape model right here is going to satisfy those desirable conditions. We want the probability to be increasing in x, right? Not a constant rate of change in our predicted probability, but something that's nonlinear in nature. And we saw visually in the prior graphs that the probability on the left-hand side never went below 0. Great. And it actually on the right-hand side never went above 1. Perfect. Now, this is also relatively easy to use because the probabilities then are tabulated according to the cumulative normal tables, which you'll find in the back of your textbook. And these are insanely easy when we're talking about calculating them within our regression software. Now, interpretation is not exactly the same as what we've done before. Right? We said with a linear probability model or anything from chapters 5 and 7, if you increase our x variable by 1 unit, it's going to increase our dependent variable by beta 1. Okay. Or with the linear probability model, it's going to increase the probability of success, or y is equal to 1, by whatever beta 1 happens to be. Here, it's different. Okay. Not exactly as straightforward. I'm going to put right here relatively straightforward. So what we have right here is that beta naught plus beta 1x is our z-value. That's what we're calling that. And then when we have our estimated values of beta naught and beta 1, we'll plug those in, and that'll give us our predicted z-value for a certain independent variable. That could be the level of the pi ratio. That could be the value of a binary independent variable. Just depends on what we're looking at. Now, whereas before we said that beta 1 happened to be the impact of our independent variable on our dependent variable in a host of different ways, here we can't exactly say that because it's going to go through a few filtering processes before we can get there. Instead, what we say right now, let me change this, is that beta 1 is the change in the z-value for a unit change in x. Okay? We're not saying necessarily that this beta 1 is going to linearly impact our dependent variable, because actually the opposite is true. It's going to be nonlinear. So we can't make this wild claim that if beta 1 is equal to 0.1, that's going to change my dependent variable by 0.1. We're no longer going there. We can say, though, that beta 1 being equal to 0.1 is going to change my z-value or my z-index by 0.1. We can say that. And once we have that, we can use then the CDF tables to calculate the effect of a change in x on estimated probabilities. Right? So it takes a few more steps to say when I change my x variable by 1 ... what is the actual predicted impact on my dependent variable? Has a few more steps in between, but we'll get there. Now let's look at what this is going to look like in Stata. So right here, we're going to tell it specifically that we have a probit model. We're going to put our dependent variable again, deny. We're going to put our independent variable here being the pi ratio. And we're always going to do comma robust just to control for the possibility of heteroscedastic standard errors. And while we won't go through this, because this is a non-linear regression tactic, this is not going to be using traditional OLS. This is instead going to be using something called maximum likelihood estimators. Okay, this is going to be discussed in section 11.3 and the appendix, but because we are in an applied class, I decided it's a little bit beyond our necessary needs. Just know that Stata behind the scenes is going to maximize what's called a likelihood. So just like linear regression, what it does is it tries to minimize the predicted errors between our actual dependent variables, y, and our predicted dependent variables, yi, by choosing the correct coefficients, right? That's what we saw in chapters 4 through 7. This is going to do something very similar, but it's going to do it in a nonlinear fashion. Right? It's a lot more complicated. That's why we're not going to do any of this by hand. Just know that it's iterating and it's constantly trying to maximize the potential of these coefficients by minimizing the errors. Right? So same idea, minimize the errors between our predicted and our actual dependent variable, and keep iterating, keep updating it until we reach a satisfactory stopping point. Right, so here we're looking at the full set of observations, 2380. And we're looking specifically at the coefficients and the standard errors here for our independent variable, which is our PI ratio. Right, so the constant happens to be negative 2.19. The coefficient on the PI ratio is 2.967. Okay, we're plugging these in right there. Right there, and we have the corresponding standard errors. Now, right about now, I might think about, saying, what is the interpretation then of these coefficients? Now, we've had nonlinear regression variables, right? We've had these nonlinear right-hand side variables where you have a variable squared or you have the natural log. That's fine. We can deal with that. But now we have coefficients that are also nonlinear, where this is entering this equation right here for the cumulative standard normal distribution in a nonlinear fashion. So we are not going to venture and say, oh, if I change the PI ratio by 0.1, this is going to lead to a beta 1 impact on my probability of denial. We're not going to do that right here, because that would only be true if the coefficient entered in linearly, which it definitely does not. Right, so what does that mean for us? The coefficient interpretation then is quite difficult. While it's true that if I increase the PI ratio by 0.1, it's going to increase the z value by 0.1 times 2.97. But I mean, what does that tell you about the likelihood of being denied? Not a lot right now, because we have to go through the z value to the cumulative standard distribution. Okay, we're in the cumulative CDF right there. We're not doing that just yet. Okay, so what we can do, instead of interpreting the causal impact of our independent variable, we're going to do the next best thing. We're going to simply wave our hands and say, for right now, what is the sign of this particular coefficient? Is it positive or negative? And then also, is this a significant independent variable? Now, for this particular example, I see the PI ratio coefficient is 2.9, and that is indeed positive. So what we can say is that increasing the PI ratio has a positive impact on the likelihood of being denied a loan. Or said in a different way, the PI ratio positively impacts the likelihood of being denied a loan, or the denial probability here. And it indeed is significant. The p-value is going to be 0.00. The z statistic right here is going to be 6.38. So we have a significant independent variable. Right, so if we were in front of a class right now, I'd be waving my arms right now. Do not try to interpret the causal interpretation of this variable. This is now entering non-linearly into our equation right here, because now we have a probit model. Do not say that increasing the PI ratio is going to change the probability of being denied by 2.96. Let's not do that. We're not going to do that here. Instead, we're going to take an alternate approach and seeing how the value, the predicted value of denial depends on different levels of our independent variable. So right now, do not interpret the causal impact of this coefficient. We are now beyond that, because we no longer exist in a world where the coefficient enters in linearly. That was the convenient days of old. Now all we can do is saying if it has a positive impact on the predicted probability of denial or negative, and if it's significant or not. Right, so that's the extent of what we can actually qualitatively say and claim at this point in time. All right, so now that we have this estimated relationship, which we have right here, again, the coefficients, the standard error is down below, and this is going to enter via the cumulative standard normal table, phi. We're going to look at the predicted probabilities, because we always want to ask, for a certain value of my independent variable, what is the likelihood of me being denied a loan or me being not denied or being approved a loan? So we can play the same game that we did with the linear probability model. Now we're going to do it with instead the probit regression. Again, the PI ratio being set equal to 0.3. What is the likelihood or the probability that I'm going to be denied a loan? So what we're going to do is we're going to plug in the 0.3 into this right here, and we're going to update this right here. We again call the z value. We're going to update the z value, and now we're going to find with our cumulative standard normal table the probability to the left of negative 1.30. So again, go back to that first table in the appendix, and we're going to find that that probability then is 0.097. All right, so according to the probit model, this suggests that if your PI ratio happens to be 0.3, the probability that you are going to be denied a loan is just shy of 10%, or 9.7%. Now, that's the predicted probability for that level. What if, however, your PI ratio goes from 0.3 to 0.4? So we're going to update the PI ratio is now equal to 0.4, and we're trying to estimate the probability of denial of our loan. Right, so we're going to plug in the 0.4 right here, and again, we're going to update our z value. Right, that's all I can say with this coefficient right here, that when I update my independent variable, my PI ratio, it's going to increase my z value by that level times 2.97. But I can't necessarily say 2.97 is going to be how my predicted probability changes. It first has to go non-linearly through the cumulative standard normal distribution. Okay, so we have an updated z value here of now negative 1.0. And we use our table in the appendix, and we find that that probability is now 0.159. So again, this says right here, if your PI ratio happens to be equal to 0.4, this says your probability of being denied a loan happens to be around 16%. Now, the question initially was, what is the effect of a change in the PI ratio going from 0.3 to 0.4? So now that probability of being denied is 0.159. It used to be 0.097. So that estimated change in the probability of being denied happens to be the difference between the two, or 6.2 percentage points. Now recall, one of the advantages of the probit model or the Loja model is this S-shaped kind of estimation curve right here. And the linear probability model, while it was super simple, it always speculated and assumed that the change between 0.3 and 0.4 on the probability level of being denied was identical to, let's say, going from 0.7 to 0.8. Here, that's not true. Here we have nonlinear effects. Right, so I did another problem outside of this lecture, and I instead didn't go between 0.3 and 0.4, like I did right here, but I instead went between 0.4 and 0.5. Right, so whereas before, going from 0.3 to 0.4 increased the likelihood of being denied by 6.2 percentage points, going from 0.4 to 0.5 increased denial by 8 percentage points. All right, so what we have right now is a nonlinear impact of increasing x on the probability of being denied. If you want to do the math at home, just to check that your application is correct, let's see, the probability of deny equal to 1 given PI ratio equal to 0.5. What you should eventually get is you should get, let me make sure this is correct, you should get 0.239. And eventually have 0.239 minus this level right here of 0.159. And that difference should give us 8 percentage points. Now, one last thing to stress before we go to the next slide is, again, the main value of probit type regression is that, number one, it satisfies the necessary conditions, so this nonlinear impact of x on the probability, and it allows for realistic probabilities, so nothing less than 0 and nothing greater than 100%. But here, we will not, stressing this enough, we will not interpret the coefficient on x. So here, we will not interpret this 2.97, but instead, we're going to look at the predicted probabilities, like we did right here, and how these predicted probabilities might change if our independent variables happen to change as well. So this suggests there is just as much value from these types of models, but a slightly different way that we utilize them when we're interpreting the results. Now, the prior slides, we're looking at our probit regression with just one independent variable. How do things change with multiple regressors? Not going to be too much of a surprise. Not much is going to change. We're now going to add, say, beta 2 x2, and we're still going to update this as the z value. Right, our goal is to estimate what is beta naught, what is beta 1, what is beta 2, given that we have x1, x2, and our dependent variable y data. And we're going to take that z value and we're going to plug it into the cumulative normal distribution via the tables in the appendix. And effectively, again, beta 1 then is interpreted as the effect on the z-score of a unit change in x1. So let's not say anything too much, right? Let's not go beyond our scopes of limitations. When we change our x1 variable by 1 unit, we say that beta 1 is the impact on the z value. We're not going to say that changing x1 by 1 unit has a certain amount of change on our, or beta 1 change on our probability. We're not going there. We first have to go to our cumulative normal distribution function table before we can actually assess what it's actually doing. Okay, so right here, we don't have anything really important changing, but it's good to just see how this might be modified with multiple regressors. All right, so now adding these multiple regressors, we're trying to mimic exactly what we did with the linear probability model. We had our y variable, we had our x1 variable being the PI ratio, and then we added a dummy variable for if the applicant was black or not. And what do we have that's slightly different? So again, we're looking at the coefficients. We're looking at their t or z stats and their p-values. Again, let me wave my hands theoretically once more, and quite literally where I'm sitting right now. Interpretation-wise, do not try to interpret the actual coefficients. Let's say on black, being 0.7. Don't interpret that as increasing the likelihood of being denied by 70%. Let's not go that route. But instead, look at the sign. The sign is positive, which means being a black applicant is going to increase your probability of being denied, and whether or not this variable is significant. And because the p-value is, well, 0.000 here, then at the 1% level, we can say that indeed, yes, this variable is indeed significant. Now, after we kind of just talk about that general interpretation, then what we want to do is measure the changes in the predicted probabilities. So we're actually going to plug in values to see how the probability of denial changes. And it's not going to be as straightforward as we saw in chapters 4 through 7, or even 8, 9, and 10, because the coefficients are not entering in a linear fashion. They're actually entering in a nonlinear fashion according to our cumulative standard normal table. So we have to be careful of what we're saying is true and what is more likely the reality. So we're going to take the same exact state output, and what we're going to do is we're going to construct a z-value according to the following criteria. So we're going to use the constant of negative 2.25. So underscore beta, so this right here, is just telling Stata saying, use the estimated intercept that we found in the prior table. And then we're going to add to that the coefficient on the PI ratio. That's what this is right here. And we're going to multiply it by 0.3, because right here we're stipulating that we want to evaluate the predicted probability when PI ratio was 0.3. So PI, which is consistent across all these examples. And we want to see the degree to which there is a predicted degree of denial if the applicant is here not black. So when that's equal to 0. And we see right here that the predicted probability then of being white and having PI ratio of 0.3, that predicted probability of being denied is 0.075. All right, so I recreated the information right here, and we just calculated the probability of denial if PI ratio is 0.3 and we have a non-black applicant, again, 0.75. And we're going to compare that to someone who's identical in every single dimension except for race. Here we're going to look at someone that is a black applicant. So that's going to be coded as 1 right there. And we're going to see that the predicted probability, well, again, don't just look at this 0.71. Again, we cannot simply just look at this coefficient and say that a black applicant is 71% more likely to be denied. That would be true if we had our coefficients entering in a linear fashion, but again, they're not. They first have to go through the cumulative standard normal table. So what we do instead is we plug in the values that we have, we update our z-value, and we evaluate it according to this table in the appendix, and we find that this probability is 0.233. So what that says to me is for an applicant who's black and who has a PI ratio of 0.3, their likelihood of being denied this mortgage loan is just north of 23%. Now, when you take the difference in the rejection probabilities, when you subtract, so we have 0.233 minus 0.075, we should get 0.158. So what that says is, holding all other independent variables constant, a black applicant compared to a non-black applicant is almost 16 percentage points more likely to be denied a loan compared to the status quo, right? So this suggests that, at least so far, if we knew nothing else, that there does seem to be some racial bias in determining whether or not someone is viable for this mortgage loan. All right, but let's take that with a grain of salt, because there's still plenty of room for omitted variable bias. Right? In this simplistic world, we're saying only the PI ratio is important, only your black or non-black status is important. No, there's probably 10 other things that are probably relevant when someone's deciding whether or not you should get a loan. Right? So we need to control for those. So it's quite possible that although there does seem to be some racial bias in the percentage of almost 16 percentage points higher for being denied a loan just by simply being a black applicant, we still need to investigate a little bit further, because if there are other variables in the error term that we are not controlling for, and we're thinking about omitted variable bias, that are, one, going to impact our probability of denial, and two, that are correlated in some fashion with being black, then this is going to mean that our coefficient on black is going to be biased, either upwards or downwards. So what that says to me is we need to be very careful with what we are claiming to be true and being valid from our model. All right, so I'm going to do right now one of the empirical exercises at the end of your chapter. This is going to be problem 11.6. All right, so we're going to use the same exact formula that we just estimated in the prior slide. I should have a quote, parenthesis right here. So we've estimated the constant, negative 2.26, the slope on PI, the slope on the black dummy variable, and in A, we're going to we're going to use the estimated probit model from 11.8, which is this model right here, to answer the following questions. So let's say we have a black mortgage applicant who has a PI ratio now of not 0.3, but of 0.35. Right? In general, just thinking about this, if your PI ratio goes up, you are less able to allocate money from your monthly income to your mortgage payments. So that almost definitely should increase the likelihood of being denied a loan. We're going to see how that's going to impact a black applicant here. So what is the probability that his application will be denied? So what are we going to do? We're going to plug this in. Let's go with A. We're going to go with probability is equal to phi. We're going to do negative 2.26 plus 2.74 times, now the PI ratio is now 0.35 plus 0.71 times 1, since we do indeed have a black applicant. And that's going to update our z value right here. So we're going to have equal to phi of negative 0.59, which would be equal to 0.2776, looking at the table, or 27.76%. So this suggests a black applicant with a PI ratio of 0.35 has a almost 28% likelihood of being denied for this loan. Now B takes it one step further. It says, suppose the same exact applicant reduces the ratio, the PI ratio, to 0.3. What effect would this have on the probability of being denied a mortgage? So what are we going to do? We're going to, instead of me rewriting this whole thing, we're going to update this right here to 0.3. And that will update our z value, or at least it should, to, this should be equal to phi of I. This should be negative 0.73. This should be equal to 23.27%. So qualitatively, what should be true is if someone's able to reduce their PI ratio, okay, this makes you more attractive as far as being able to loan you money from the bank's perspective. This should reduce the likelihood of you being denied a loan. And that's what we see right here. This individual was able to lower their PI ratio to 0.3, and their probability of being denied went from about 28% to just over 23%. Right, so this question is asking what is the effect this would have on the probability. But we go from, let's see, we go from 27.76 minus 23.27. That's going to be equal to about 4.5 points. So said all together, if we have a black applicant that's able to lower their PI ratio from 0.35 to 0.30, they're able to reduce their likelihood of being denied by 4.5 percentage points. All right, now let's do the same exact thing with C. Right? It should be the case that when you lower your PI ratio, you should have an easier time in getting a loan, or your likelihood of being denied should go down. Now, for a black applicant, it went down 4.5 percentage points. Let's see what's true with a white applicant. Right? If there was no bias at all in the approval or the denial of a mortgage loan, then this should be relatively similar. Let's evaluate that. So with C, we're going to repeat this. We're going to do the same exact thing. We're going to go with, so the probability of deny, given that X is equal to 0.35, and that we have black is equal to 0 since we have a white applicant. This will be equal to phi of negative 2.26 plus 2.74 times 0.35 plus 0.71 times 0, since we have a white applicant here. And what we'll find is that this probability is going to be 9.7%. And then we do the same exact thing for someone who's actually able to reduce their PI ratio from 0.35 to, let's say, 0.3. Then we have the new probability. But that's going to be equal to, if I did this correctly earlier, this is going to be 7.5%. So the net change then is going to be equal to 9.7 minus 7.5, or 2.2 percentage points. Comparing that to 4.5. Now comparing apples with apples, a black applicant with a PI value of 0.35 and then a non-black applicant with a PI ratio of 0.35, we see we're comparing these two numbers, 27.76 and 9.7. So just by this dimension alone, this suggests that the black applicant is almost 3 times more likely to be denied simply because of their status right there, their demographic status. And when you look at the new probability, we're comparing 23.27 to 7.5. Again, almost actually more than a 3%, a 3 times higher likelihood of being denied, assuming the same exact level of the PI ratio, simply for being black. All right, the net change here is 4.5. The net change here is 2.2, and we see that there's a differential impact depending on the demographic status of the applicants. So then answering this last question, does the marginal effect of the PI ratio, so decreasing it from 0.35 to 0.3, does it depend on race? Well, this says 4.5, this says 2.2. One's almost twice the amount of the other one. I'm going to say yes. Yes, it does. So we say then, indeed, that the marginal effect does indeed depend on the level of the probability, which in turn depends on the race of the applicants. So this would indeed suggest that we don't have mortgage lenders exclusively thinking about the financial aptitude of applicants to pay back a loan. Instead, we have the real possibility that there might be some racial profiling going on in the selection process. All right, that is the end of this first portion of the Chapter 11 lecture. In the next portion, we will discuss the empirical example, and we'll also dig into logit regression.